So in Lab 7, you are going to be looking at cellular respiration. You're going to be doing two experiments in this lab. One is going to be about fermentation, where you're going to be looking at yeast's use of sugar. And the other, you're going to be looking at aerobic cellular respiration, which means oxygen is going to be needed. So for that experiment, we are going to have to do just a little bit of math with our final data. So I want to take a second to actually walk you through that. So in your second experiment, you are going to be using peas in a big chamber, basically sitting in test tubes, to measure how much oxygen is actually used by those peas. So remember, peas are plants and they are also the seed of the plant, which means they have a lot of sugar built in them and they can actually take in oxygen from the environment around them. Not like breathing like we do, but they still have a diffusion of oxygen into the peas. So in order to go through aerobic cellular respiration, you have to have sugar and oxygen, which is two things that these peas will have during this experiment. So now what we need to do is to find a way to measure how much oxygen is actually used by these peas. And that can be directly correlated to how much cellular respiration that these peas can actually do. So in this experiment, you are going to be testing to see if peas go through more cellular respiration in a warm room temperature environment or in an iced environment. So in your classroom, you're going to have 6 different tubes, or 6 different groups really, running this experiment 6 different times. So each group will just have to do one experiment. But then you're going to have to tally all your data together and get a nice average to really represent what's going on with these peas. So I am going to run through an example here of just the math of how you are going to get to a number that tells you how much oxygen these peas actually used. So I am going to be starting this. Make sure I got my pen going. I'm going to do this example at room temperature. Okay, so room temperature is about 20 degrees Celsius. So you will take this measurement in the lab of the water that's actually in your chamber. So 20 degrees Celsius, it's right around 70 degrees Fahrenheit, which is about normal in our lab. So you set this up at room temperature and you are going to let it run as it is explained in your lab book. So when you look at that beautiful picture that's in your lab book of what this whole thing looks like, you are going to have 3 test tubes and you are going to have 3 capillary tubes that are attached to those. So after some time to equalize the environment, you are going to close off the tubes altogether. So you are going to close the top clamps so that no air can get through there. And then you are going to plug the capillary tube with some dye. That dye is going to block the entrance of air coming into the tube. So we can actually measure it. Basically, that dye is there to measure. So as the peas take in oxygen, they are going to pull that dye closer to them. So during this experiment, you are going to measure how far the dye moved. So for the sake of this example, I'm going to say the first test tube of peas moved its dye 8.2 centimeters. And the second tube of peas moved its dye 6.1 centimeters. So these are the 2 representations of your 2 experimental groups and how much oxygen or how much air they're really pulling into them. Also remember that in this experiment you have what's called soda lime that will be sitting on top of the peas, and that soda lime's job is basically to suck up any of the air that the peas might release, specifically the carbon dioxide. So remember, as you go through cellular respiration, oxygen is taken in and carbon dioxide is released. So in order to make sure that that carbon dioxide doesn't mess with this dye movement, we actually absorb it with the soda lime, and this will mean that the dye movement should be accurate. Without that soda lime, not accurate. In fact, I've actually seen the dye get pushed out of the tube because there's so much pressure and carbon dioxide that's actually pushing away from the oxygen being taken in. So make sure you include your soda lime. So the first thing that we have to do here is to find an average of our movement, because do remember that the more data we have, the more accurate our data really is. So the first thing we have to do is take our P calculations and take an average. So P's, taking an average, most of you know how to do this just fine, right? You take P1 plus P2 and you divide it by 2. So in this case, that is 8.2 plus 6.1, and we divide that by 2. So 8.2 plus 6.1 gives us 14.3, and we'll divide that by 2, which means we are at an average of 7.15. So that is the average amount of air that was moved into the peas. Again, we'll interpret that as oxygen actually being moved into the peas. But you also have to run one more tube while you're doing this, and that is going to be filled with beads. I mean, literally little plastic beads are going to be inside of this test tube. And what that is going to act as here is our negative control. So we have two experimental tubes with the peas in it, and then we have a negative control for the beads. Because beads obviously should not go through cellular respiration, right? They're not alive, no energy needs to happen for these beads. But what we actually do see is that occasionally there is a change in the dye movement here as well. And basically what that accounts for is all of the rest of the stuff that's going on in the room, right? So it's not just about air movement. Maybe it's about pressure in the room, or changes in the doors even being open, or maybe one of your classmates hit the board that all of these are taped to or something. We need to account for that. So if the beads move, we have to address that. So maybe the beads won't move and you'll have a 0 number here, but more than likely you'll see something happen here. So for the sake of this example, we are going to say that the beads moved 1.2 centimeters. So the bead actually saw a dye movement towards the beads of 1.2. That means something. So we have to account for that. So in order to calculate our net movement, we need to take our average minus the beads. So we will take 7.15 minus 1.2. So 7.15 minus 1.2 gives us a total of 5.95, which we will put into this box here. So now we have our net movement, right? That's how many centimeters that the dye moved for our experiment, right? With all of the data kind of taken into account. But that is not the question that's actually being asked in this experiment, right? The experiment is asking how much oxygen did the peas actually consume. So given our experiment, the way we set it up, and the size of the capillary tubes that we have in the lab, we have a calculation that for every 1 centimeter of dye movement, it's 14, it's not 1. For every 14 centimeters of dye movement, there is 1 milliliter of oxygen gas that is used. Okay, so for every 14 centimeters of dye movement, there is 1 milliliter of oxygen that's used. So we need to do that conversion here. So we're going to take our 5.95 and convert that into milliliters. So to find the calculation of milliliters, we are going to say milliliters of oxygen is equal to 5.95 centimeters times this conversion. So we will multiply this times 1 milliliter over 14 centimeters. So now from here, you're doing your algebra, however you do your algebra. Honestly, I just get rid of the 1 because 1 times anything is itself, right? So I basically think about this as 5.95 divided by 14. So here's where you need to keep track of your units, right? So this is 5.95 centimeters times milliliters now, right? Because we multiplied it times 1. And this 14 is your centimeters. So the centimeters will cancel out, right? And we're left with the units of milliliters, which is important here because that's what we're actually trying to find up here for our table, right? We're trying to calculate into milliliters. So 5.95 divided by 14 on the calculator will give us a total of 0.425 milliliters of gas. And that's what you would put here. So 0.425. And this is your answer that you are going to share with your class. So you'll notice that table 7.3 in your lab book is going to be a collection of all of the data in the class. So every group that's running it, again, at most you will have 3 groups running ice bath, and you will have 3 groups running the room temperature. We're going to have to collect all of that and average it. So you'll average together your totals for your room temperature and then for your ice bath. So remember, average, you just add them all up and divide by the number. So in this case, if you have 3 groups, you will add all 3 groups together and divide by 3. That'll give you an average. And then you're going to compare the averages, right? Did you see more oxygen that was consumed at room temperature or more oxygen that was consumed in the ice bath? Basically, where was cellular respiration more effective, at that room temperature or in the ice bath? And we are going to use all of the data in the class, because remember, the larger the sample size, the better that our data is going to be. The more replicates that we can get out of that, obviously, then can help us confirm things even more. So more data is going to mean a more accurate data set for our whole experiment, so that we can interpret that to help us support which temperature is going to be more efficient for these growing little peas to survive best.